All right, 111 students, let me look at the second half of the exam. And so here is the question 11, and I printed out a hard copy here. But you have these three pieces here, and so let's call this, number 11A here. And if you remember, it says we have four equal charges of little q, and they're 3.25 millicoulomb, and they lie on the corners of a square. And then there is a fifth charge of value q and 6.23 microcoulombs. And so remember that micro is 10 to the minus 6th, and milli is 10 to the minus 3. And I put a couple of hints along the way for you. So anyways, I hope those helped. And it's directly above the center of a square at a height equal to the height of one side of the square. And the sides of the square and the height of q above the square is, and then they give this number, 2.54 millimeters. Determine the Coulomb force on q. And then there's a little hint. You can get the distance by using Pythagorean's theorem, and you can get angles by using your trig functions. And I got inverse tangent, but truth is you can use inverse sine or cosine. Also, you can use the symmetry. You only need to find the force on one pair and then multiply by 4. So let me take that second hit into consideration and draw something that looks like this. Then that if I have the little q here and we move out towards the center of the square and we go up here to capital Q, this is a height d, and that these two each have a positive charge, so there would be a force pushing like this. Now, it's a little easier to see in this three-dimensional looking graphics, but maybe you can imagine the one I'm drawing is like from this front Q to here, and so the force is kind of back towards the corner. It's also pointing up, and I just am going to use the idea of the symmetry that this one would be forcing up like that, and this one here would be forcing up something like this. This one's kind of hard to draw. This one's kind of coming out of the plane, something like that. But they're all twisted up at the same angle. I guess they'd sort of look like this if I took maybe, I don't even know if I can hold 4 different markers. I'll do 2 of them kind of up at an angle. Here's a third one, and if you could imagine a fourth one here. And so all 4 of these are kind of pointing up, and they're along the diagonal. So the stuff along the XY plane would cancel off. And so the idea here is that the force total would only be in the upward, if you call that the z direction. And that's what this part says using the symmetry. And in fact, if you found the z component for just one of them, you could multiply by 4. And that's a big part of this problem. And so I would say that, maybe half the problem right here I've already done in terms of just looking at the symmetry of it. And so the symmetry goes a long way. And what it means is I don't have to worry about an x component, a y component, but I do need to do a z component, and I only need to do a z component for one of them. And that's what I'm trying to draw here. And let's see if I've got some different color I could put on here. Well, I'll do this. This little piece would be in the plane. And so this would be part of the XY plane. And then this little piece would be the part of the Z direction. And so there's some angle here. And so I would say here that the total force is 4 times this z component. And if we call this the magnitude of z, then we're looking at the piece that is opposite. So it would be sine of that. So, like I said, this is really half the problem. Just realizing that the two things I really need to calculate are the magnitude of this force. And maybe I shouldn't even call it z. Maybe that's confusing. Maybe I should just call it 1. So I need to find just the magnitude of one pair. Then when I multiply it by sine theta, so I have to find theta, I get the z component and then just multiply that by 4. So once I do that, now let's just kind of break the two pieces in together. Let's just find the force between these two guys. And so here is the distance between them. And we know that it's got a vertical height of d, but here's where it could also get a little tricky here. That would be this diagonal distance. Let me come back to the picture. So if I'm thinking of this as one of the pairs, it would be this distance. And so we'd be asking ourselves, you know, how far is that? You might say that it's half the whole diameter. Because if you look at the diameter, we've got, you know, the diameter of a square, which is d by d. And then we're going to take its diameter. Well, let me kind of draw that picture here. And so I have something that looks like this. See, and they told me that the D was, where is it? 2.54 millimeters. So 2.54 millimeters. And this is 2.54 millimeters. So that means this distance right here, call it a c, because c squared would equal to, and we can first do our Pythagorean's theorem along here to figure out what c is. So 2.54 squared plus 2.54 squared, and then, oops, and then taking the square root of that means we're looking at the diameter of 3.59. Now, as I said, we need to cut that in half, and so c over 2 would be 1.78. Okay, so this distance here is sorry, I think I rounded that the wrong way. Yeah, 1.80, sorry. 1.80. So this is 1.80. And that's from here to here. Okay, so then we're going to go up D so we can get this distance along the diagonal. Okay, and so that's what I'm hunting for. Let me just call it R for the distance away. And so coming over here to my picture, I can now say R squared is 1.8 squared plus 2.54 squared. And so I'll grab my calculator, square that, add it to the 2.54 squared. And then this is a 9.68. That would be R squared. And I guess I will take the square root. I was kind of hesitant because I'm going to just square it later on. but it might be just nice to have something to work with. All right. So there's a big piece of this puzzle, just kind of figuring out what that distance is. Because coming back to where I got started is I was trying to say, what is force number one? And so it's Coulomb's constant times each of the charges divided by r squared. So for this particular problem, it would be 9 times 10 to the 9th for Coulomb's constant. The capital Q is 6.23 microcoulombs. The little q is 3.25 microcoulombs. And watching my units, this would be 3.11 times 10 to the minus 3 quantity squared. And so that's going to give me the magnitude of that force between them. So grabbing my calculator, 9 times 10 to the 9th times 6.23 times 10 to the negative 6, 3.25 times 10 to the negative 6, divided by 3.11 times 10 to the negative 3 quantity squared, gives me a force of 18,840 newtons. Now, like I said, that's the magnitude, so that's going to go back into that equation. Looks like I'll need another piece of paper here. Looking at this angle that we talked about, which would be the same as this angle down here, I could use sine or tangent. Maybe I'll do tangent here, because the tangent of the angle would be the 2.54 millimeters. That's the opposite. Over the adjacent, 1.80 millimeters. And now I can solve for the angle. So, well, let me just do the ratio first. 2.54 divided by 1.80. And so that ratio is 1.4. Let me then do the inverse tangent of that. And we're looking at an angle of about a 54.7 degrees. All right, so final, last step here is to say force total is 4 times, and then number 1 down here is this 18,840. And then the sine of 54.7 degrees. All right, so 4 times 18,840 times sine 54.7, and I get 61,504 newtons. Nice. And there's the answer to the first one. Find the force. And notice I, did these little hints here. All right. So there's a good one and a hard one. I hope you did well on it. Remember, there is partial credit. So scan through this and, see what you've done. It could be as simple as just some geometry wrong. That's not so bad. It means I'll be looking a little more carefully at your physics. And are you kind of seeing the symmetry here, that it's 4 times one of them with the component of the sine of the angle? Not so much the geometry here of getting those, but that's an important piece of it, but not as important as the physics of it. All right, well, with that in mind, let me put that aside and move on to the second one. All right, 11b. So 11b says, let's go ahead and study this circuit. And they give us our resistances and our voltages. And we're asked to find the current in each of them and also the voltage. And so maybe the thing I would do first is start looking at an equivalent. And maybe I'll just put in some numbers also. Let's see, the voltage they said is an 18. Resistor R is 75. I guess I drew a bent first. But then the big thing is it goes down this way right here at 3 times 75. So 75, 150, 225. So this is going to be 225. And I guess the one I want to do next is to say, well, it would flow through here and around. So these are in series. And so the 2R and the 4R make 6R. And so I'm going to have something that looks like this. And so I would say this is my first equivalent circuit. And again, it's 6 times 75. So what is that? 450? Maybe I better just check that. 6 times 75. Okay, good. Now, I would probably then also do the next equivalent one, which, recognizing that these two then are in parallel, I would do 1 over 225 plus 1 over 550 equals 1 over the equivalent. So let me take the, and there's a couple ways we can enter in our calculator. Maybe the easiest way is to go 1 divided by 225 and add it to 1 divided by 450 and then just hit enter. And then take the reciprocal of that, and we're looking at 150. So 150 is the equivalent, 150. All right, and then maybe one more step. Since these two are now in series, I would just add them, and that's 225. And that's really kind of the key to our equivalency problems, is to say that the ultimate question is to understand each of these four. That's where this is going to come in. But that circuit is equivalent to this one or this one or this one. And so use whichever one will help you solve the problem. And I guess this is really easy, because if you look at this one right here and just apply Ohm's law, you're going to say the current coming out of this battery, V over R, is just 18 divided by 225. So you're going to do something like this, 18 divided by 225, and get 0.08. And so using this equivalent circuit, you're going to say the current coming out of the battery is 0.08. And then if you jump back to the real circuit, you'll see that what comes out of the battery goes to this number 1 right here. So 0.08 would be the answer to what comes out of here. Now, sadly, it comes up here in splits. So the current in number 4 and the current in 2 and then 3 have something less than that. But I do know that they have to add up to 0.08. That can be useful. I also know that the current in number 2 and number 3 must be the same because they flow here. Now, in fact, I will kind of use that to my advantage by saying something like this. Since we just solved this one and this one's equivalent, we could then do something along these lines, that this right here would be the same voltage as along here. And I guess I might do it this way. Why don't I figure out the voltage here first? Because if I compare this equivalent one back to here, the voltage on this 75 right here would be whichever current this is, which would be the same as this. So voltage equals to IR. So that'd be 0.08 times a resistance of 75. So 0.08 times 75. So that comes out to be 6 volts. So this is 6 volts. Now, I didn't give myself much room here, so maybe I'll fit it in here. But remember, the Kirchhoff's law is we got to add this around and get 0. So this is an increase of 18 and then a decrease of 6. So this must be another decrease of 12. See, and why that's helpful is if we look at this equivalent circuit and come back to the same thing, what we're saying is this voltage right here is that 6. And then this, which is really these two branches right here, each have 12. So resistor 2 and resistor 3 each have 12 volts on them. Oh, my apology. I did not mean to say that. Sorry. What I meant to say, sorry, is that this branch is equivalent to 12. So the combination of 2 and 3 is a 12. But also number 4 is a 12. That's what I meant to say. And then using Ohm's law, if we know any two of these, we can find the third. And so I'll just say right here, applying Ohm's law to this line right here, I've got my voltage of 12 divided by my resistor here of number 4, which is the, right there, the 3 times the 75. So that is a 12 divided by 225. And so that is a 0.053 repeating. Now, remember what we said earlier, another one of Kirchhoff's laws, whatever current comes in here, okay, so we just said that was 0.08, and it splits off, and so in this case, it splits off as 0.053 this way. The rest of it must go that way. And that's the current then that is in 2, and since they're in series, it's also in 3. So that would be the 0.08 minus the 0.053. So grabbing my calculator and taking the 0.08 and subtracting that number, we get our 0.02, and I'll just round it to a 7. And then they're the same. And then the last step would be to say, remember, if you have any two of these, you can find the third, because V equals to IR. So right here, number 2, which would have a resistance of, did I ever write down? I guess I didn't write down resistor number 2. That would be 150. And then 4 times would be 300, which is when we added them, we got the 450. Okay. But I can just take then that current that is in number 2 and multiply it by the 150. And so that's a 4 volts. And then I can do the same thing with number 3. I can take the current here that is in number 3 and multiply it by the 300 ohms, and I get 8. And good, the two voltages here, the 4 and the 8, add up to the 12. And what's nice about these kind of problems is you can kind of check to see if you've done it right. For example, you can say, okay, the current coming out of here is 0.08. Okay, so if that's right, then it splits. And so these two, the one going through number 4 and the one going to number 2, should add up to that one, and they do. And then because these are in series, 2 and 3 should be the same. Okay, that's good. And then if you take a loop like this one, here an increase of 18 should equal a decrease of these 2. So these 2 should add to 18, and sure enough, the 6 and the 12 add up to the 18. Or if you do the big loop, you got 18, and then this is the 6, and then this one and this one. So if you go around these 3, so the 1, the 2, and the 3 should add up also to 18. And so the 1, the 2, and the 3 should add up to 18. And they do, and that's how we got there. All right, so good. So again, a lot of details there. Hopefully you were able to get most of the details. And so notice I did equivalent circuits. We learned 2 techniques, so you could have done this with Kirchhoff's laws, but I, for whatever reason, thought that equivalent circuits might be the way to tackle that one. All right, now let's get on to the last one, which is C. And the first part of C is real easy, or relatively easy, but B is probably the hardest one on the test here. So we're going to study this on the right. We got these 2 wires. The 2 wires are parallel, and they carry the same current. And so we've got the current going upward. The distance between the wires is 1.25 centimeters. Both wires are very, very long, and so we can use that magnetic field from a long straight wire. What is the direction and the magnitude of the magnetic force on a 5 centimeter long segment of the rightmost wire? So maybe I'll just kind of mark the 5 centimeter. And I probably should have done that in the diagram for you, because I did do it down here in B, the 5 centimeter segment, when we have the current at 90 degrees. I'll give you a little hint, and if you go to chapter 22, section 10, they do this step. They say the force is the current times the length times the magnetic field that it's in. And that's going to help us get direction as well as magnitude. Okay, but I guess I'll start with the idea that let's just do the calculation of the magnitude. Now, to do the magnitude, we need to say something like this. I'm trying to find, I'll call this wire number 2 and this wire number 1. I'm trying to find the force on number 2. And so it would be the current in number 2 times the length of number 2, but it would be in a magnetic field that's created from number 1, and then there would be the sign of this angle, which, if you look at this section, this was the special case where they're 90 degrees. And let's come back and talk about that 90 degrees here, because we need that when it has to do with direction. Okay. Well, maybe I should mention it in passing here. All right, so this is the right-hand rule. So if I take my right hand and I grab wire number 1 with my thumb pointing up, the fingers represent the field. So that means on the left-hand side of the wire, the magnetic field would be coming out. Then it would arc over the top and go in. And so over here where wire number 2 is, it's going into my piece of paper here. And so the current is going up and the field is going in, and that's a 90-degree angle. That's what that sign of 90 is. It says, hey, what is the angle between the field and the little wire segment? And so that's why I put the 90 degrees. Now, the other piece of this is that we learned that the magnetic field from a long straight wire is given by this equation. And so the magnetic field is created by current number 1. And so current number 1 is making this magnetic field. So the force on number 2 would actually be a product of these 4 things across the top. Current number 2, the length of number 2, mu naught, and current number 1. And then it would be divided by 2 pi, and then r being the separation between the 2 wires. So you can start the problem right here, and I have a feeling that most of you are going to do that. I haven't started the grading yet, but I suspect that many of you will, start right here, because that's where my hint is. My hint says is go ahead and look at section 10 of chapter 22, and this is exactly the steps, I guess 4 steps that your author goes through. So for this one, you can kind of just plug in your numbers. And so the current is the 7.58 amps. The length of the wire is 0.05 in terms of meters. So let me be careful with my units, because it does say what is the magnetic force on a 5 centimeter long segment. Okay. Mu naught was the 4 pi times 10 to the negative 7. And then, of course, current number 1 is the same as number 2, and I'll just save myself a little bit of writing by putting a square there. It's divided by, and then here's a 2 pi. I'll just put the 2 pi here, but then save me some calculator work and just cancel off the pi's and reduce the 4 down to a 2. Now, the R is still here, and the R was, I believe, listed in centimeters, so I need to be a little careful. Yeah, 1.25 centimeters. So 0.0125 meters. All right, so just kind of plug and chug to get this first part. Here is the 7.58 squared times 0.05 times 2 times 10 to the negative 7, then divide by 0.0125. And so we're looking at 4.60 times 10 to the minus 5 newtons. Okay? So there's the easier of the two. Where it gets harder here, and there's a little hint here to kind of help you out, is now you're going to take these same 2 wires, so we have the same current, and now you're going to lay them perpendicular as shown. What is the direction? Oh, let me pause. I didn't really finish this. That's the number. What's the direction? And the direction of the force would be to actually do this cross product. So I know I spent some time just figuring out what the direction of the field is. So the field is down and the current is up, and then I just said they were 90 degrees. But I didn't finish with the right-hand rule. So let me take my right hand and put my finger in the direction of the current, and my thumb, sorry, in the direction of the current. And then my fingers need to go the direction of the field. Okay? And then the palm is going to give me the direction of the force. So the force would be towards the other wire. And we talked about that and how the currents in a straight line or in moving together tend to pull the wires together. So these wires have a magnetic effect of pulling together, whereas wires that have currents in opposite directions tend to rip each other apart, but these pull together. So there's the direction, and so maybe I should put here not only the magnitude, but I should put the direction and say it's left. Okay, so I'm glad I mentioned that because we kind of have the same thing going on here, where it says, you know, get the direction and the magnitude of the force on a 5 centimeter right here long segment of this horizontal wire that begins right here when you're 2 away. So that means it ends when you're 7 away. Begins 2 centimeters from the mortal. Hint. Think of this 5 centimeter long horizontal piece as millions of small microscopic pieces. Okay, so let's do this. Let's call a little microscopic piece, and we'll use the calculus notation, dx. And so that's going to produce a little microscopic force, df. And so this is the big step right here, to say if I'm looking at just one microscopic piece, there would be a little bit of force. So there's my df. That corresponds to a little bit of length. So there would be current number 2, then there would be this microscopic length of dx. We would have mu naught, we would have current number 1, we'd have a 2 pi. And then, of course, to add to the complexity of it, the force depends on how far away you are. And so if you think about each little microscopic piece, the first little microscopic piece is going to be a distance of 2 away, and then it gets a little further, 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 and then eventually it's 7. So that distance here, which in problem A, or part A, we called it R, maybe for here I'll just call it an X, because that's, you know, how far away that microscopic piece is. So that's kind of what I was trying to help you with here, and it says here, think of the magnetic force on one small microscopic piece, kind of like we just did in part A. And then using our calculus, add up all these microscopic pieces to get the total. So in other words, integrate. Because if you remember, the definition of an integral was this summation of an infinite number of small little pieces. And so anytime you want to add up an infinite number of small things, you get this calculus symbol. That's why Newton took the letter S and elongated it for a sum of a lot of pieces. All right, so now we can maybe put our limits that we're going to end up starting at the first microscopic piece of 0.02 and going to our last microscopic piece. Now, before I do any of this calculus, I better be careful with hint number 2. It says this must be done with calculus. Okay. Since the magnetic force on the vertical wire gets weaker with distance away, you can't use some kind of averaging effect. And so this is the advantage of calculus. This is why we do calculus. This is why Newton invented calculus. He could not do physics without calculus. He was trying to do physics and realized that he needed to add up infinite number of things. In his case, he was doing velocities and kinematics, but he realized he needed to add up an infinite number of different changes of velocity to get the overall change in velocity. And so that led him to this new mathematical technique, which today we call calculus. And so that's exactly what this problem is trying to do. So by far the hardest one on the problem. Hopefully you did well on this, but let me actually solve it. So the integral of df is just f. That's good because that's what I'm trying to find. And then in terms of actually doing calculus, things that are constants can be removed from the integrational symbol. And that tends to help it look nicer and easier. And now I have an integral that I can do. And it's one of the common ones with the natural log. So this is going to be current 2 mu naught current 1 over 2 pi. And this would be then the natural log of x evaluated from 0.02 to 0.07. And now I can put in my numbers here. So let's put in the currents. The current's the same as before, the 7.58. And if you'll let me save a little bit of writing, both current 1 and 2 are the same. Mu naught is the 4 pi times 10 to the minus 7, which when written over the top of that 2 pi reduces down to a 2. And then this is going to be the natural log of 0.07 minus the natural log of 0.02, which even that we can simplify into a quotient, but I don't think there's any point in taking the time and looking at the properties of logarithms. I'll just put it in. In fact, I'll do that one first. And so let me grab my calculator here and go natural log of 0.07. And subtract natural log of 0.02. All right, so that is about a 1.25. And then I will multiply that by 2 times 10 to the negative 7. And I will multiply that by 7.58 squared. And get a force of 1.44 times 10 to the negative 5 newtons. And I was just going to say, if I can compare these, this is substantially lower than that one. And that makes sense because, I mean, the beginning part of this wire is 2 centimeters away. That's further away. And then all the other pieces are even further away. So, yeah, I expect this to be quite a bit lower, and sure enough, it is. Now, the very last thing is to get the direction. Maybe I'll change colors here, but using the right-hand rule, which gives me the direction of the magnetic field. So from this vertical wire, if I grab or imagine grabbing the wire with my right hand with my thumb going up, the field would arc around here, and so it would be going in on this side of it and out on this side, which is the same thing we did in part A. So nothing different here. Of course, what is different is now the current going horizontal instead of vertical. So when I do this right-hand rule for this cross product, so like we did up here, here we said the current was going up and the field was in. Now we're going to say the current is going right and the field is in. So taking my right hand and putting my thumb in the direction of the current and my fingers in the direction of the field, which would be down into the screen here, my palm is then pointing upward. So the force here is going to be up. So maybe to finish this, I'll say up. So I've got the direction and I've got the magnitude. So again, hope you did well with those, or at least mostly well. I will, look for your thinking, look for your logic, and realize that there's a lot of pieces involved here, and so lots of partial credits, and looking forward to getting started now on grading these. And I hope that you self-graded this all the way through and that you also corrected any mistakes or misconceptions you might have had. All right, take care.